Thanks. I believe we're ready to begin. Thanks very much, everybody, for joining us today. I'm just going to run through some housekeeping rules, and we'll get started very shortly. So joining us today, we have some people who are completely new to FluidFlow, some existing customers, and also some sales partners or distributors. We would request that you would send any questions via the chat function, and we will respond later on by email. This is due to the fact that this is going to be a 30-minute webinar. Okay, so James, if you want to take it from here.
Okay, perfect. Thanks, Brian. Okay, so it's James McClune speaking. I'll take you through the rest of the presentation. Just to let you know, the session is being recorded and you'll be able to view the presentation afterwards from our website. The slides, the presentation slides that we go through today will also be available, and we also have a relief valve sizing document which you can view from our website. Okay, so just to give you a little information on ourselves, our address is shown on the left hand side. We have a toll-free number and our direct telephone number, and also our email address is support@fluidflowinfo.com, so you can contact us afterwards if you have any queries in relation to any specific system design issues you may have. Just to give you an overview of FluidFlow before we get started on auto sizing. FluidFlow is quite unique in that it's one product which allows you to model fluids in various phase states. So you can model your gas flow, liquid flow, two-phase flow, slurry, so settling and non-settling slurry flow. You can perform thermal energy heat transfer analysis, and that's included in the product, and dynamic analysis or scripting. So that allows you to perform what-if type scenarios and model your system as it performs in reality. Okay, so if I just move on to the next slide. So today's webinar session is focused around automatic equipment sizing and sizing of relief valves in particular, but let's just look for a moment to see what other elements we can automatically size within FluidFlow. So you can see we can size pipes based on either a design velocity, a design pressure gradient, or an economic velocity, which is calculated automatically by the software. You can size your pumps and fans by design flow rate or design pressure rise. You can size your control valves, so the software will calculate the CV based on a design pressure or flow rate for the system. You can size your orifice plates based on a design flow rate or pressure loss. And the same applies to your venturi tube and your nozzles. And finally, at the end, your relief valves and bursting discs can be sized to API and ISO standards, and you can automatically size these devices for liquids, gas, steam, and two-phase systems. Okay, so that's just a little brief overview of the automatic sizing. So considering relief valves in particular then, so why do we really need to size our relief valves? Well, obviously we need to determine the correct effective discharge area of the relief device required to protect the process equipment. We want to evaluate the diameter of associated or connected inlet and outlet piping. We also want to consider the fluid phase state at the inlet and outlet of the relief valves, and obviously apply the appropriate pressure loss correlations. And we also want to ensure that the required mass flow rate can be passed through the relieving stream, and also evaluate the pressures in the system. And what FluidFlow does is it allows you to model the interaction of connected components, whereas in some cases we have been discussing with engineers where they may have been using Excel or other platforms to perform relief valve type calculations, but that only looks at the device in isolation, not connected to any other equipment. So FluidFlow overcomes that little obstacle for you. Okay, so today we're going to focus on 3 example cases, and we'll build one simple model, and we'll model each of the 3 cases from that base network. Okay. So the first one then, it's a hydrocarbon system made up of butane and pentane. And this is based on an example in the API standard around, I think it's page 44. Okay, so the required hydrocarbon vapor flow rate is given as 53,500 pounds per hour. It's a mixture of butane and pentane. The molecular weight is 65. The relieving temperature is 348 Kelvin. And the relief valve is set to 75 psi gauge. Back pressure is also given at 14.7 psi absolute, or 1 atmosphere. And also we've got our permitted accumulation of 10%, our relieving pressure 670 kPa, the compressibility 0.84. This is automatically calculated by the software, so we don't really need to worry about that. We've got CP over CV, again calculated automatically by FluidFlow. Our KB value, or back pressure correction factor, of 1, and a capacity correction factor for the rupture disk, again 1. Okay, so let's build a base model of this system in FluidFlow. So let's place a tank onto the flow sheet. We'll use a known pressure node to define the outlet pressure, and then we'll place a relief valve onto the sheet, and we'll use steel piping to connect up the various components, like so. I'll just turn on my pipe reference numbers here, and now I can edit the information, the default information I should say, for my various elements. So if we look at the tank, the default fluid is water. If I wanted to change that, I could just simply access the fluids database, and I can choose from any of the 1200 fluids in this database, or I can add my own fluids. And that's something you only need to do once, and it will be stored for all your future projects. So we have a hydrocarbon mixture, so let's go about creating this new mixture. So I select database, open the fluids database, select new mix, and give it a title. So we'll call this fluid webinar mix. Select OK. I can define the gas mixture by weight or mole percent. We'll just choose weight. I'm going to fix it in gas phase, and it's butane and pentane. I'm just double clicking to add these fluids. So the butane then, in order to get a matching molecular weight from the API example, is 48%, and the pentane obviously must be 52%. So that gives us this total percent sum for the fluid of 100% at the bottom. Select OK. The fluid has now been added to the database, and the critical properties estimated automatically by the software. You can see gas density in this case is using Benedict-Webb-Rubin equation of state. Okay, so I've now assigned this fluid to the database, and now I needed to assign it to the model. So very quickly, assign the fluid to the model, and now I can set about defining my design conditions. So the inlet pressure was 97.2 psi absolute. So I'll just scroll through my pressure units. Temperature was 348 Kelvin. Okay, I can just leave some of these default parameters because they're not so critical. I'll move on to the relief valve, and we're going to automatically size it so that feature switched on. The pressure loss model, in this case, is the API standard, but this is where we would choose ISO if we wanted to use that particular approach. The maximum allowable working pressure over pressure allowance. Sole device was 10% in this case, but you can also choose multiple devices or external fire case. The set pressure then was 75 psi gauge, like so. Design flow rate was 53,500 pounds per hour. And the KD discharge coefficient was 0.975. The outlet pressure was 1 atmosphere, and it was given as static pressure. And finally, I need to define the input information for my pipe. So in this case, let's make the length of this pipe quite short. Let's make it 1 inch from the top of this vessel, and the downstream pipe will make it 1 foot. Now I've edited the lengths of both of these pipes here, but I can also edit the diameter, and I'm going to multi-select these components, and I can hold the shift key and select as many pipes as I need to. I can alternatively select all the pipes like so, and I can edit the diameter for all elements I've now selected in one go. So I'm going to change both pipes to 6-inch schedule 40 in this case. Select calculate, and now you can see the flow direction is shown throughout the model. If I look at the results, you can see now that the calculated size and size at maximum allowable working pressure is given. In this case it's 3178.7 millimeters squared, which matches very well with the API standard example case, which worked out to be 3179 millimeters squared. You can see it's a gas system, so at the in and outlet of the relief valve that I have selected on the flow sheet, you can see the fluid is in gas or vapor phase. You've got your stagnation and static pressure, your velocity, your Mach number, temperatures, density, Joule-Thomson coefficient is taken into account, and your composition mass at the bottom is given, 100% webinar mix in this case. But you'll also notice here that the standard orifice size, so the next closest size match from the available API standard sizes is also given for us here. So this is just suggesting orifice size P, so we might want to consider that size of a orifice in this particular example case. So we could go off then to a vendor, get the relief valve data, access the relief valve database in FluidFlow, and define a new relief valve in the database and model that particular vendor device in the system. And you can see there's some sample lesser manufacturer types already in here. Okay, so you can expand this database. Okay, so that's just the first sort of example case. So we have seen how to create a new mixture and model using the API standard. So if I return just for a moment back to the presentation slides, now I'm skipping over a number of slides here, but obviously you can work through these if you wish after the webinar. I'll just click through them here. Okay, so there was the API standard results. It was 3179 millimeters squared, and we have 3178.6. Okay, so let's move on to the second case. So it's a two-phase propane system, again solved to the API standard. And the following information has already been provided for us. The required volumetric flow rate is 100 gallons per minute. The relieving temperature at the relief valve is 60 Fahrenheit. The relief valve is set to 260 psi gauge. Back pressure is 10 psi gauge. The density is given at 31.92 pounds per feet cubed, and this is calculated automatically by the software anyhow. Permitted accumulation, once again 10%. The relieving pressure is given 300.7 psia. Back pressure correction factor is 1. Discharge coefficient is 0.65 since the propane is subcooled in this case. So I can return to my original model. I can change my fluid from the webinar mix fluid that we created. Select propane. Okay, we have assigned propane to the model. And now we just edit the design input information. So it's 300.7 psia and it's 60 Fahrenheit is the temperature. And again, the default information we can just leave as is. Go back to the relief valve. It's the API standard. It's a sole device, 10%. Set pressure, 260 psi gauge. And the flow rate was 100 gallons per minute. So it's down at the bottom here. It is US gallons per minute. Okay. KD in this case was 0.65. The discharge or the outlet pressure, I should say, was stagnation pressure or total pressure, and it was 10 psi gauge. Okay. If I want to edit the pipelines, I can click back here and I can change this, for instance, to 1 meter in length. I can change the second pipe to also 1 meter in length. And now I can calculate to refresh the results. So let's look at the results. Again, the calculated size and size at maximum allowable working pressure is given, 133.7 millimeters squared. The software suggesting the API standard size F, which we can see is 198. The fluid is in liquid phase at the inlet of the relief valve. The pressure, velocity, etc. is also calculated. density, but you can see we've got flashing occurring across this relief valve, in which case now the fluid is in two-phase at the outlet, and all physical properties have been calculated accordingly. If I look at the downstream pipe, you can see once again the fluid is in the two-phase state. The vapor quality is shown 0.27, and that vapor quality is increased ever so slightly at the outlet of that pipeline, obviously because we've got some additional liquid foil boiling off to form additional vapor in that line, so the vapor quality increases ever so slightly. The software has solved this pipeline using the Friedel pressure loss correlation, and just on that, if I select options, calculation, two-phase, there's a little drop down tab here showing you all the two-phase correlations which are available to choose from. Okay, so if I look at the chart, you can see the system resistance curve and the duty point on the curve for your pipes and elements. And we don't have any warnings in this case, which is obviously a good thing. Just on the relief valve, if I go back and look at the results, so the result units here are all shown in metric, but I can change to US units by changing environment set, and now you can see the calculated size is shown in inches squared, flow rate in pounds per hour, and I have edited some of these values to show bar absolute. Velocities in feet per second, temperature in Fahrenheit, etc. And if I just have a look at density, I can just display density and fluid phase state at the inlet, for instance. And you can see 31.64 was the density calculated at the inlet of that system, and we had 31.92 in the API standard calculation. The API standard also gave us a size of 0.207 inches squared, so it's an exact match in this case. Okay, so let's return to the slides for a moment once again. And again, you can work through that example. You can see the finished example case shown here. We'll move on to example 3. This is an ethylene relief system to the ISO standard. Again, we've got the required flow rate given, 4,200 kilograms per hour. Relieving temperature, 55 degrees C. The relief valve is set to 55 bar gauge. Back pressure, static pressure is 36.1 bar absolute. The relieving pressure, 61.51 bar absolute. The KB is 1. Discharge coefficient is 0.721. Again, I can simply come back to this model, change my fluid once again. I'll just scroll down to find ethylene. Here we are. Change my input information, so 61.51 bar absolute, like so. Temperature, 55 degrees C. We'll keep these values. Move on to the relief valve. It's solved to the ISO standard. It's the sole device once again. Set pressure in this case was 55 bar gauge, which is up near the top. So bar absolute and bar gauge. The flow rate was 4,200 kilograms per hour. And the KD value was 0.721 and KB was 1. The outlet condition then was 36.1 bar absolute. And again, I can come back and edit some of my pipe lengths. I can change the inlet pipe to 1 inch in length and the discharge pipe to 1 foot, millimeter, whatever it happens to be. So now I can recalculate to refresh my results, change my units to SI once again. And you can see for the standard orifice size we have no predefined sizes, and that's simply because we're using the ISO as the pressure loss model, which unlike API doesn't have a list of standard orifice sizes predetermined. So that's why that information appears like so. The size is 113.2 millimeters squared, which again is a very good match for the worked example case. You can see this is once again is a gas system. We've got flow, so the actual flow rate in the system shown at the top here, and then we've got flow at standard and normal temperature and pressure conditions. So this information is all worked out automatically for us. Again, we've got our inlet velocities, Mach numbers, etc., density, Joule-Thomson coefficient, all calculated for us. Okay, so that just really gives us an overview of how you can use the one product to, I guess, automatically size your relief valves for various different design scenarios. And accurately sizing your relief valve, you avoid the risk of oversizing or undersizing, and obviously with oversizing comes the risk of the system failing or not performing properly, and the additional cost of oversized relief valves needs to be taken into account. Something I should just point out when I think of it is that the software, we mentioned the discharge coefficient KD and KB. Well, the software automatically will determine if a viscosity correction factor is required and apply the correct value accordingly. And FluidFlow will also model relief valves in your steam system, so the capacity correction factor, or KSH, may be applied depending on the actual steam condition. And so for saturated steam at any pressure, the KSH would be 1. So all that information is taken into account behind the scenes automatically by the software. Okay, so that pretty much concludes the little examples. Just to finish off on the slides, you can just see here some of our existing users who use the software to both automatically size relief valves and model manufacturers' relief valves in their system to clearly identify how the system will perform. There's a little testimonial here towards the end if you would like to have a read at that. So I guess the question is, do you have a particular design scenario that you need to look at sizing your relief valves correctly? Do you want to evaluate the performance of a manufacturer's relief valve in your system, or do you need to automatically size your pipes, pumps, control valves, orifice plates, etc.? So the software will let you take a total system design view, allow you to evaluate alternative design scenarios. It accelerates your design program and removes the guesswork from performing your relief valve calculations. You can contact us at support@fluidflowinfo.com, and if you need to, you can also avail of a free trial which is available. If you need to use the trial or obtain a free trial, you can contact us at sales@fluidflowinfo.com. If you have got a technical query, you can call us or contact us at support@fluidflowinfo.com, and again, these contact details are available at the end of the slide. If I just return to our website for a moment, you can visit future webinars from the resources section, and you can also avail of a free trial by filling out the form on our website. So simply your first and last name, company details, give us some information on how you currently go about your designs. Click the little option here to confirm that you're not actually a robot, and you can start your free trial, and we'll get you up and running quite quickly. Once again, if you have any questions, you can always contact us at support@fluidflowinfo.com. Okay, so we hope you found the today's session of interest, and we look forward to speaking to you again soon. Thank you very much for attending.